We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow.
Okay, so in the curriculum of electrical machine 2 E501, we are discussing about module number 3, and the topic was special machine. Okay, and this is my outcome or objective of this module. So let's start. The special machine hysteresis motor. So today we will study hysteresis motor. Okay, so hysteresis motor. Now hysteresis motor is basically fall in the class of fractional kilowatt motors that basically runs at synchronous speed or almost very near to synchronous speed. Okay, so hysteresis motor is synchronous motor with the uniform air gap without DC excitation. So a hysteresis motor is basically a synchronous motor with uniform air gap and without DC excitation. So this is the definition of hysteresis motor. It is basically a synchronous motor with uniform air gap and without DC excitation. Okay, and this motor may operate from single phase or three phase supply. That means stator winding of such a motor has either 3 coils as in a 3-phase motor. So stator winding can have 3 coils such as 3-phase motor, or at least 2 coil, or at least 2 coils such as single phase motor, single phase AC motor. In both cases, the basic requirement is that the stator must be able to produce a rotating magnetic field in the air gap. So the basic criteria is the production of RMF in air gap. Okay. The rotor. The hysteresis motor has two parts. One is stator and the another part is rotor. And the rotor is basically of cylindrical structure. Cylindrical structure. Okay. And in a hysteresis motor, torque is produced due to hysteresis and eddy current induced in this cylindrical rotor. So the torque is produced due to hysteresis and eddy current induced in this rotor. Okay. Now construction. So first, the stator construction. The stator of a hysteresis motor is similar to that of a induction motor, with the basic requirement that it produced a rotating magnetic field. So the stator is similar to a induction motor, with same as it has a criteria that it should produce a RMF, rotating magnetic field. Thus, the stator of the motor can be connected to either a single phase or a three-phase supply. We know that three-phase motor produced a more uniform rotating field than a single-phase motor. For a single-phase hysteresis motor, the stator winding is a permanent split capacitor type. For single phase, it is permanent split capacitor type, or of the shaded pole type for various, or it can be shaded pole type for very small sizes. In case of the permanent split capacitor type, the capacitor should be used with an auxiliary winding in order to produce an uniform field, such as which we have seen in case of single phase induction motor. So in this permanent split capacitor type, this capacitor is basically used to produce an uniform field. Okay. Now the rotor construction. So this is a representation of a cylindrical rotor structure of a hysteresis motor. It consists of core of aluminium. So the core is made of aluminium, or it can be of other magnetic material, okay, which carries a layer of special magnetic material, and the outer layer has a number of thin rings. The outer layer special magnetic material, we can show it here, hysteresis ring, thin ring to form laminated rotor. Okay, in smaller motor a solid ring may be used. So in smaller motor we used solid rings. Thus the rotor of this hysteresis motor is a smooth cylinder, as we have mentioned earlier, and it doesn't carry any winding. So there is no winding, that means there is no bars, as we have seen in case of induction motor. Okay, so this is the structure: smooth cylinder, permanent magnet alloy material, and non-magnetic support is there. Okay, and the ring is made of special magnetic material such as magnetically hard chrome, magnetically hard chrome, magnetically hard chrome, or cobalt steel, having very large hysteresis loop. Okay, so this is the hysteresis loop. Okay, and this relationship between this induced magnetic flux B and the magnetizing force. So this relation between B and H is represented by this hysteresis loop, and a ferromagnetic material that has never been previously magnetized or has been thoroughly demagnetized will follow the dashed line, this dashed line, as the H increased. Point A, all the magnetic domains are aligned, material has reached to the point of magnetic saturation. So this is saturation point. H is reduced to 0, the curve move from point A to some point B. Some of the magnetic domains remain aligned, but some have lost their alignment. So this point is known as retentivity. Okay. Magnetic force is reversed and the curve reached to the point of C, which is known as coercivity. Okay. And magnetizing force is increased in the negative direction, so it will reach the point D. So this is also known as saturation in the opposite direction. Okay. And then it will reach to the point E and F respectively. Okay. Now reducing H to 0 brings the curve to point E. It will have a level of residual magnetism equal to that achieved in the other direction. Increasing H back in the positive direction will return B to 0. So this is the hysteresis loop. Now operation of this hysteresis motor. Now what happened when a three-phase supply or a single-phase supply is applied to the stator, a rotating magnetic field is produced, and this rotating magnetic field magnetizes the rotor rings. So a field rotating magnetic field is produced, and this magnetize rotor rings and induces poles, magnetic poles within it. Induces poles in it. A uniform cross-section rotor inherently will match the number of stator pole. So that means if the rotor has uniform cross-section, it will inherently will become equal to the number of stator poles. So number of stator poles equals to number of rotor poles for uniform cross section rotor. Okay, and this induced rotor flux lags behind the rotating stator flux because of the hysteresis loss in the motor. So this is also we have to keep in mind that induced rotor flux lags the rotating stator flux. So induced rotor flux lags the rotating stator flux because of the reason of hysteresis loss in the rotor. Now the angle delta. So if we see here, so this is the angle delta, H or delta. So the angle delta between the stator magnetic field Bs and the rotor magnetic field Br. So this is my this is my PS, suppose, and rotor is there, suppose, and this angle is delta. Okay, is responsible for the production of torque. So this angle is responsible for the production of torque. So rotor poles follows the rotating flux but lags behind angle del H. Okay. So this angle is between stator and rotor magnetic field is responsible for production of the torque. Okay. Now the angle delta depends only on the shape of the hysteresis loop and it is independent of frequency. Okay. For this reason, a magnetic material having a wide hysteresis loop should be used. So that's why we used cobalt steel, because cobalt steel has a wide hysteresis loop. So we have to keep this in mind. So the material we should use for hysteresis motor, that should have a wide hysteresis loop. Thus the coercive force and the residual flux density of the magnetic material should be large. And ideal material should have a rectangular hysteresis loop. So this one. So ideal material. So this is the ideal material. It has a rectangular hysteresis loop. This is the widest hysteresis loop. Okay. Ordinary steel are not suitable as they are resemble to loop 3. So this is loop 3 is resemble to ordinary steel. Cobalt vanadium type material are used as they have loop. This is 2 for cobalt vanadium. Okay. So this 2 which is approximated to loop 1. Okay. So now, in addition to stator magnetic field produces eddy current in the rotor, this eddy current produces their own magnetic field. So again this stator field produce eddy current in the rotor, and which in turns produced its own magnetic fields. Thus there is an additional torque on the rotor due to this eddy current. So there are two torque exist, one for hysteresis loop and one for eddy current field. Okay, and the eddy current loss is given by this equation. We know PC equals to Ke F2 square B square, where Ke is a constant, F2 is frequency of eddy current, B is the flux density, but F2 equals to SF1 we know from induction motor, where S is the slip and F1 is the stator frequency. So the equation becomes this: P equals to K A square F1 square B square. Similarly, the torque will given by this power by angular speed. Okay, so this is the torque. So we can write it down. Torque equals to K dash A. So K dash equals to K E F1 square B square by omega S, because P equals to this Ke A square F1 square B square by S omega S. So this Ke F1 square B square is this constant K dash. So it will become Te equals to K dash S. Okay. Now torque due to hysteresis loss. And hysteresis loss we have, when we have studied transformer, we know this is represented by this equation Kh F2 B to the power 1.6. This 1.6 is cos 10 mesh constant. Okay. And we will put in place of F2 SF1. Similarly, we get torque due to hysteresis loop, that is K double dash, which is a constant. So it is clear that the torque is proportional to slip. So we got for hysteresis motor, torque is proportional to slip. Therefore, as the speed of the rotor increase, the value of torque decrease, which we have seen in case of three-phase induction motor speed control using rotor resistance. As the speed of the motor reaches synchronous speed, the slips becomes zero and the torque also becomes zero. As the electromagnetic torque is developed by the motor is because of the hysteresis loss and remain constant at all rotor speed until the breakdown torque. At the synchronous speed, the eddy current torque is zero and only the torque due to hysteresis loss is present, because we know tau h is K double dash is a constant. So when it will reach the synchronous speed, the slip automatically becomes zero and torque will also become zero. And at the synchronous speed, this eddy current will become zero because slip equals to zero. Because we have seen eddy current torque is equals to K dash S. So S will become zero. So this will become zero. Only this torque, this constant torque will remain at rotor speed until the breakdown torque reaches. Okay. And this is the torque versus speed characteristics for hysteresis motor. So this curve 1 is ideal curve, but the practical hysteresis curve will follow this dotted line, and deviation from ideal characteristics is due to the presence of harmonics. So this deviation is because of the presence of harmonics. So torque is constant at high speed including synchronous speed. So this torque is constant at high speed including synchronous speed. Okay. And these are the advantages of hysteresis motor: smooth, vibration free operation, low noise, positive starting, constant torque, steady state speed is directly controlled by electrical input frequency. Okay. And disadvantage is low efficiency, low power factor, low power and hunting phenomena, which we have seen in case of three-phase induction motor. And the hysteresis motor is generally used in electrical clocks. We should remember this, timing devices, tape decks, and other precision audio equipment. So basically hysteresis motor used in audio equipment. Okay. So this is all about hysteresis motor. Okay. So this is all about hysteresis motor.